Yeah, hello everyone. My name is Rajal Mukherjee, and I will be conducting this live session for NPTEL course on computer organization and architecture. Like every week, we will be solving some sample questions which are related to this week's material. So, it will be interactive, and please feel free to ask any question in the chat. So, let's go to the first question. So, first question is, consider a five-stage instruction pipeline with stage delays of 20 nanoseconds, 25 nanoseconds, 35 nanoseconds, 30 nanoseconds, and uh, and 22 nanoseconds respectively. The delay of interstage registered stage or interstage register stage of the pipeline is 2 nanoseconds. The total time required for the execution of 100,000 instructions will be. So just consider. Uh, can you hear me right? You can hear me right? Yeah. Okay. So so it is said that we have a five-stage pipeline. So consider this as the stages. Uh, so consider these are the five stages. So first stage, takes 20 nanoseconds. It says 25 nanoseconds. Second stage 35, 30, and 22. Other than that, between every stage, there is a delay of 2 nanoseconds. Like between every stage, like these stages. So, so if you consider, like what will be the clock period? So first thing we need to understand what will be the clock period. Clock period of the pipeline. So in most examples you have seen in the in this week, you will see that each like most of the questions are like that every pipeline stage has an equal delay. But if it is an asymmetrical delay, then we need to choose the max of these all delays. So what would be the max of 20, 25, 35, 30, 22? Plus there is this 2 nanoseconds extra delay for each stage. So it will come out to be 35 plus 2 equal to 37 nanoseconds. So basically the clock period is basically chosen as the stage which has the maximum delay. In this case it is the stage 3, 35 seconds, plus the 2 interstage delay, that is 2 nanoseconds. So total number of stages now, it is given as 5 stage, it is a 5 stage pipeline. So the total time required will be for 1000 instructions will be k minus 1 plus 1000 into 37. K in this case is 5, so that is 5 minus 1 plus 1000 into 37. It will come out to 3715 148 nanoseconds. So if we convert it into milliseconds, it will be 37.148 milliseconds. So like if you ask me why this is happening, it is a very uh, it is a concept that is quite common. uh, Let me explain it. So suppose we have a uh, five 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 stage like delay, five stage pipeline. So in a five stage pipeline it will be one first instruction. So this is like suppose instruction 1. The next instruction, so these instructions get over at 1 2 3 4 5 fifth second, fifth like unit time, 5 second. Let us consider. Next instruction gets over at like if this happens, next instruction will get over at 6 second. Instruction 3 will get over at 7 seconds similarly. So similarly the fourth will get over at 8, and last one, that fifth, will get over at 9. So if you check after the first 4 seconds, for first 4 seconds there is no completion, but after that every second one instructions is getting completed. Fifth second one instructions get completed, sixth second one instruction gets completed, seventh second one instruction get completed, 8 seconds one instruction gets completed. So that is how this formula comes, k minus 1 plus 1000. That is the time that will be required for completion of 1000 instructions. From there this formula comes. So ultimately this is the answer, 37.148 nanoseconds. It will ultimately come down to 37.4 ms, 37.148 ms. That is the answer. If you have any doubt, you can ask regarding this. Question 10 of week 8. So see, one thing is that I cannot discuss the assignment questions. This has been told to me like that, like this has been my instruction. So if that has been like, so what is the question, like have you asked in the forum regarding it? Because the forum is the place for that. So here I need to discuss the problems for this week. So if you have any doubt, you can ask in the forum regarding that. Yeah, just send me the question on this chat. I will check. Okay. I will reply. Just remind me at the end. I will have a look at it. Just inform me after 7. I will do it. Okay. Question 2. So any doubt regarding the first question, you can ask once. I will give some time regarding it. Do you have any doubt regarding question 1? Okay, I will go to the next question. So question 2 is, consider a three-stage instruction pipeline with stage delays of 25 nanoseconds, 30 nanoseconds, and 50 in nanoseconds respectively, and the delay of an interstage register stage of 5 nanoseconds. Suppose the pipeline is modified by splitting the first stage into two simpler stages with delays 10 nanoseconds and 15 nanoseconds. 15 nanoseconds, and the second stage into two simpler stages with 15 nanoseconds and 15 nanoseconds. For the execution of 1000 instructions, the speed up of the new 5-stage pipeline over the 3-stage pipeline will be. So it is said initially we have a initially we have a 3-stage pipeline. So in the 3-stage pipeline, we have delays of 25, 30, and 15. Next, in the next, it has been told that we are splitting the first and the second stage into 10, 15, and the next stage into 15, 15, and 15. So what is the execution speed after this? And also it is given that there is a interstage delay of 5 in both cases. So for this, what is the time period, like clock period? Clock period is max of 25, 30, 15 plus 5. That is 30 plus 5, 35. And what is the execution time? Execution time is 3 minus 1 plus 1000 into 35. And what is the clock speed here, like clock period here? That is max of 10, 15, 15, 15, 15 plus 5. That is 15 plus 5, 20. And what is the execution time then? 5 minus 1 plus 1000. This formula comes from the previous one. So what will be the speed up? Speed up will be this divided by this, right? So if you look at this, it will be 1004 divided by 35 into 20, 1002 divided by 1004. So it will, if you calculate this, it will roughly come out to be 1.746. So if you have any doubt regarding this, you can ask. Like this problem comes specifically from the previous one, like how we solved the previous one. Specifically, it comes from that, and like these are very standard questions for like this topic. Yeah, I will repeat. So, you did you have any doubt in the previous questions? Those who have asked, like this comes from almost the previous question. So, if you have any doubt regarding the previous question, I can uh, repeat that also. Okay, so the like main concept of this comes from the previous question. So if you see here, you have given a 5 stage instruction pipeline with delays 20, 25, 35, 30, and 22. So the clock period of this pipeline is actually the one with the max time consuming. So because if one takes 20, another takes 25, another takes 35, we need to take the one which has the maximum like clock time, which takes the maximum time, so that one operation, it does not happen like that one operation takes small time, another time takes long time. It has to be equal for this pipeline process. So it comes out to be 35 plus 2, 37. So 2 is here the interstage delay. So 37 is the clock period. Now consider what is the total time for 1000 instructions. Like here it is mentioned how much time is required for 1000 instructions completion. So total time for 1000 instruction is basically k minus 1 plus 1000. 1000 is the number of instructions. K is the stage delay. It is a 5 stage delay pipeline. So 5 minus 1 into plus 1000 into 37. It comes out to 37.148 nanoseconds. So I explained how this formula derives k minus 1 plus 1000 thing. So consider this is a 5 stage pipeline. So instruction 1 gets over at 5 seconds. Like fifth unit of time, 1, 2, 3, 4, 5. Fifth unit of time, the first instruction is completed. Now similarly, if the second instruction will get completed, if it is a 5 stage delay pipeline, at 6 unit of time. Third instruction will get over at 7th unit of time. Fourth instruction will get over at 8th unit of time. And the fifth instruction will get over at 9th unit of time. So if you check, like from 5 second onwards, every second one instruction gets completed, right? So the only thing is, this is the extra time period that is required. So that what is this 4 is the extra time that is required. After that, every instructions get completed in 1 second. So every instruction gets completed in 1 second is 1000 plus this 4, right? This 4 will be added on. So that is what 5 minus 1, 5 is the stage delay. So there comes from there comes this formula k minus 1 plus 1000. Next, if you look at this problem says that initially you have a 3 stage pipeline. Each delay is 25, 30, and 15 nanoseconds. 25, 30, and 15 nanoseconds. So we found out the clock period, that is the max of 25, 30, 15, and also it is given that it has a 5 nanosecond interstage delay. 5 nanosecond interstage delay. Now if you check, so next is this ext, that is the execution time. It will be actually k minus 1, that is 3 minus 1 plus 1000 into 35. This is the execution time, right? Next, it is said that the first stage is divided into 2 smaller stages, that is for the 5 stage pipeline, that is 10 and 15, and the second stage is divided into 2 smaller parts, that is 15 and 15. So what will be the maximum clock period? Maximum clock period, we devise the how it is done. That is the maximum clock time for one stage, that is in case 15, and the 5 second is the delay, interstage delay. So that will come out to 20. So what will be the execution time? 5 stage pipeline, that is 5 minus 1 plus 1000 in the time required for each instructions into 20. Why 20? Because it is given the clock period, right? So what will be the speed up? Speed up will be this CP, suppose ext1 divided by ext2. So speed up will be ext1 divided by ext2. This will be the speed up. So that we are calculating here, and that value will come out to 1.746. Now it is clear. Okay, so let's go to the next problem. So it is given, consider a non-pipeline CPU working at 1 gigahertz clock. The frequency of ALU, branch and memory operations are 50, 25% and 25% respectively. If ALU and memory takes 4 cycles and the branch operation takes 7 cycles, the average instruction will be how many nanoseconds? So it is given, it is a non-pipeline CPU, frequency is 1 gigahertz, that is 10 to the power 9 hertz. Now what is clock period? What is the clock period, or the time is 1 by frequency, that is 10 to the power 1 by 10 to the power 9 seconds, that is 1 nanoseconds. Right, now it is given what will be the average instruction time. So execution time will be, so what is the percentage of ALU instruction? That is 50%. 0.5. How much time the ALU instruction takes? 4 given. Then how many branch instructions are there? 0.5. 0.25, sorry. Then how many cycles does it take? Branch takes 7. Then how many is the memory instructions? 0.25. And how many cycles does it takes? 4. So basically what, so into 1 nanoseconds, right? So what will be this? So if we calculate, this will come out to be 2 plus, this one is 1 and this one is 175, that is 4.75 ns. Any doubt regarding this? These are straightforward, like what happens in and this is a this question demonstrates what is the how it is the difference between a pipeline and a non-pipeline CPU. In a pipeline CPU, like only a part of the instruction get executed at each stage, whereas in a non-pipeline CPU, entire execution, like entire process needs to be executed at the same time. So here is one of the simple such example, that so the instruction time requires all the process. So if it was a pipeline, then the operations like ALU operation will be separate, memory operation will be separate, branch operation will be separate. But if it is a pipeline CPU, non-pipeline CPU, all will be executed at once. Any doubt regarding this? Okay, so let's go to the next question. So again, it is said that we have a non-pipeline processor, consider a non-pipeline processor with a clock rate of 6 gigahertz. Average cycle per instruction is 10. The same processor is upgraded to 6-stage pipeline processor, and but due to internal pipeline delay, the clock rate is reduced to 2 gigahertz. So assume there are no stalls in the pipeline, the speed up achieved in this pipeline processor will be. So we have a non-pipeline processor and a pipeline processor. So in the non-pipeline, it is said for like for one instruction frequency 4 gigahertz. Okay, just a second, 1 minute. Sorry, that was question number 5. So question 4 is, which of the following statement is or are true? Pipeline hazard prevent pipeline from operating at maximum possible speed. Option B, data hazard arises due to resource conflicts. Option C, control hazard arises due to branch and other instructions that change the PC. PC in this case is program counter. So let's like consider each statement one by one. So A, pipeline hazards prevent pipeline from operating at maximum speed. You know that due to like hazards, what happens? So there are data hazards. So as a hazard, there are stalls in the pipeline, right? And due to the stalls, the like the pipeline doesn't work at its maximum possible speed. So option A is true. Option B, data hazard arises due to resource conflicts. So this is false. Data hazards occur like when there is a data conflict. So suppose two registers access like same data register being accessed by two separate instructions. Suppose there are two instructions, inst1 and inst2, and both require access to one is reading register R1, another suppose writes register R1. So this creates a hazard. So due to this data hazard occurs. Due to resource conflict, data hazard does not occur. Due to resource conflict, structural hazard occurs. And option C is like control hazard arises due to branch and other instructions that change the PC. This is true. Control hazards occur when there is a branching related issues. So A and C are true. B is false. So now let's come to this question which we are seeing. So consider a non-pipeline processor with a clock rate of 4 gigahertz and the average cycles per instruction of 10. So for one instruction, so for non-pipelined, frequency is 4 gigahertz. Therefore, clock period will be 1 by 4 into 10 to the power 1 by 4 ns. That will be 0.25 ns. Next, it is said, so it averages average cycle per instruction is 10. That is, for one instruction, 10 cycles are required. Therefore, what will be the execution time for one instructions? 10 into 0.25, that is 2.5 nanoseconds. So this is for non-pipelined. Next, it is said the same processor is upgraded to a 6-stage pipeline processor, but due to the internal pipeline delay, the clock rate is reduced to 2 gigahertz. So for the pipelined, it is said f is equals to 2 gigahertz Therefore, what will be the CP? 1 by 2 ns, that is 0.5 ns. Now, what will be the execution time? Execution time will be C. In case of a non-pipeline, every procedure like that, fetch instruction, memory read, ALU, all this takes a single execution, like one has to be executed at a time. Whereas what happens in case of pipeline instructions, like I have demonstrated here. What does this happen? So like after a stage, at each time unit, one instructions get executed. So per stage, one instruction gets executed at each clock cycle. So it will be 1 plus 1 into 0.5 ns. That will be 0.5 ns. Therefore, speed up will be 2.5 divided by 0.5. That will be 5. Any doubt regarding this? So this comes like, so ideally in a pipelined setup, each instruction is executed in one cycle. Okay, so like the so if you consider this number, this this number in with respect to this is very small, this is very small. So suppose if you are like executing 10,000 instructions, 10 lakh instructions, then this number is useless, like it is a very small value. So we can just assume that each instructions, like that mathematically it is almost equivalent to one instruction getting executed at one cycle. So there, from there, this observation comes that like ideally in a pipeline setup, each instruction is executed in one cycle. Any doubt regarding this? Okay, so let's go to the next problem. So we have been given these four instructions: add R2, R5, R8, mul R1, R4, R5, sub R9, R2, R6, and add R1, R2, R6. So between all of them, like we such assume that it is a five-stage like instruction pipeline. So what like where are the like which between which of them RAW data hazard occurs may occur. So what are the instructions? Add R2, R5, R8, mul R1, R4, R5, sub R9, R2, R5, add R1, R5, R6. So what is read after write instructions? That means a read is getting executed while a write is also occurring at some other instructions. So if you look between these two pair, 1 and 2, are there any common registers? No. Like these users 2, 5 and 8, these users are 1, 4 and 5. Next, between pair 1 and 3, are there any common register? Yes, R2, R2. One is read, another is write. So uh, RAW occurs between 1 and 3. So this is a write, it's a read that is occurring after a write. So this is one pair. Now let's continue the process between 1 and 4. Are there any common register? Yes, R5. But in this case, both are read, and read after read is it is not a hazard. Next, let's look at the pair of 2 and 3. Are there any common register? Yes, R5, and these are also read after read. And between 2 and 4, R1, but this is also a write operation. This is also a write on R1. This is also a write on R1. So it will be a write after write between 2 and 4, and between 3 and 5, it is R5 is common, and that is also a read after read, which is not a hazard. So which is the only read after write hazard? 2 and 3. So 1 and 3, sorry. So the correct answer is B. B is the correct answer. Any doubt regarding this? You can ask. Yeah, the one who has raised hand, you can speak. I have given the microphone.
No, I can't understand, sir. Could you explain one more time, sir?
Which one?
The option 2 and 3 also the read and write operation is working there.
Option 2 and 3. How, which one is the read operation? You say.
How we can identify, sir, whether it is a
So,
read
so,
instruction is
so,
executed?
so you understand this is a right like a three address code, right? So first one is the like so you this one is clear, right? Like what does this mean?
Yes,
This
sir.
add art.
This one, sir.
So suppose this one. So what does this mean? R1 is basically R4 into R5, right? So R4 and R5 are the operand, and R1 is the place register where we are writing the uh, result.
Yes, sir.
So you check let me go again. So between 1 and 2, are there any such registers common between R and 2, 1 and 2? No. Now
I
you
can't understand, sir, how add after that the sub instruction is executed. That is a RAW
so you know what is RAW, right?
that leads to the data hazard.
So it is a read after write data hazard. So what is a read after write? So if you look at this statement like 1 and 3, so what are the data we have? R2, R5 and R8. So basically it is a add of R5 and R8, and the data is being stored at R2. In 3, what is happening? We are reading the value from R2 and R5, that is we are subtracting R5, R2 minus R5, and we are storing it in R9. So you see the this operation is a write operation on R2, whereas this operation 3 is a read operation on R2. So this is a read after write, right? So this is a read and this is a write on the same operator, on the same register. So that's why we are calling it a read after write hazard. Now, if you are telling me that why not 2 and 3? See, in 2, R5 is also in read mode. We are using the R5 in read mode. So what does this mean? This is R1 is basically R1 is equals to R2 into R5. And in 3, R9 is basically R9 is equals to R2 minus R5. So in both cases, R5 are used as an operand, so it doesn't matter, like it is a read after read, so read after read, so this doesn't change the value of R5, so that's why it is not a hazard. Now if you look at the statement 2 and 4, what is happening? We are writing the value on R1 in statement 2, and in statement 4 again we are doing the same, writing the value on R1. So that's why it is a write after write hazard. Now you understand. Anyone has any doubt regarding this? Okay, so let's go to the next question. And this is a continuation of previous one. So it is said we are executing these three instructions: LW, R5, like load instruction, add instruction, and sub instruction. So how many stall cycle will be required for this? So what are the 5 stages of pipelining? So one is instruction fetch, instruction decode, instruction fetch, decode, execution, memory, write back. Right. So let's consider it for these three instructions. IF, ID, EX, IF, ID, EX, W. Okay. So if you check, there is like, if you check only one data item, that is only one we have a possible RAW, RAW of like hazard possible, only one RAW hazard possible, that is between 1 and 3. Is clear? This is here, it is an like, here it is a data which where we are storing it, and here it is an operand. So this here we are in statement 1, in instruction 1 it is operating at write mode, and R5 in instruction 3 is operating as a read mode. So this is a read after write hazard. Between 2 and 3 R8 and R8, but it is a read after read, so no issue, that is not an hazard. So 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 what happens in 3? In statement 3, it is basically R3 is basically R5 plus R8. And what does this add operation occurs? Add operation occurs in this execute phase. So this happens in this execute phase, right? So so the value of R5 and R8 must be present by this stage. It has to be present to the ALU. So this happens in ALU. So this has to be present by this stage, by this stage. Now notice the first instruction. So instruction fetch, instruction decode. What does this like is basically what happens in instruction 5? Like, it's basically memory operation of 2000 and R2. So this memory, it gets stored in R5. So where does this addition occurs? This addition occurs here. Where does this memory operation occurs? This memory operation, it occurs here. So basically this value of R5 is available in this point, and it is the same point where it has to be present. So let me use a different thing. So by this point the value of R5 is present, and by this point the value of R5 is needed for instruction 3. So definitely we do not need a stall in this case, because the data is available to the CPU at the correct time. So hence in this case it will be a zero stall cycles required. Any doubt? I can explain again if you want. And these are very important questions. Okay, so let's go to the next one. Okay, so which of the following data hazards can cause performance degradation in a MIPS 32 integer pipeline? Var data hazard, WAW data hazard, RAW data hazard. So this, in theory, raw is called a true dependency, true data dependency. So this always causes a stall in the pipeline, whereas WAR, WAW are called false dependency, and specifically the reason for calling them false dependency is because they can be avoided by register renaming. So basically, if you modern compilers basically use two different set of registers. If they detect whether there is a write after write instructions or a WAR war data hazard, if that happens, they basically do a register renaming operations where each of the registers are renamed, um, against which the war or WAW dependency occurs, and that avoids this data dependency. So that is not considered, that does not cause any performance degradation in a pipeline. So only option C is the correct answer. That causes true degradation. Yeah, the question difficulty will be like this. So the questions which I am discussing now are mostly like, if you have followed these tutorial classes, mostly they are questions which are asked in the exams or assignment questions, type of questions. So that will be the level. Also, these are very standard questions that are asked in like, mm, for the course of computer organization. So like this it will be, and these are very like simple questions in that sense. Like whatever I discussed today, those are very simple. Mostly like finding data hazard type, what is the pipeline execution time. These are very simplistic questions that will be asked. So let's go to the next question. So it is said we have a we have a pipeline which has a CPI of 1.5. Assume there are 30% of all instruction executed that are branch, out of which 90 are taken branches. So there are 30% branch, 90% are taken. So if the pipeline predict taken and the if pipeline does not predict taken, what will be the branch penalties? So pipeline speed up if the so let's consider for predict taken. So like branch penalty in both cases, if predict taken or non taken, is basically 1. That is the minimum penalty that will always be taken. So speed up will be 5 divided by 1 plus 0.3, because for the branch taken. And for predict non taken, branch penalty will again be 1. Branch speed up will be 5 divided by 1 plus 0.3 into 0.9. So this will come down to 3.85, and this will come down to 3.9. So this is a very like a very like question which is to show you like what happens if there is a branch prediction unit, and what kind of like speed up you can expect if there is a uh, like if it is a branch taken or a branch not taken approaches. So let's go to the last question. This is a very important question. So in a MIPS pipeline with branch target buffer, assume 85% branch are found in BTP, 15% are not found in BTP, 15% are prediction taken, and 75% are the prediction are 50% of the prediction are incorrect, and 75% of the branches are taken. So let's make a table. Present in BTP, prediction, correct. Yes, prediction correct is yes. So it can take two steps, either it will be a taken branch or it will be a non taken branch. Present in BTP, no. Present another case will be present in BTP, yes, and the prediction is not is a prediction correct is false. So that will be the another case. Again, that will have a case of taken and non taken, and then is the third case where it is not present in the BTP. So what will be the branch penalty cases? present in BTP misprediction not present in BTP misprediction not present in BTP taken branches. But let me clear it once. This is a little confusing. Branch present in BTP misprediction plus branch not found in BTP taken branch plus branch not found in BTP not taken. So if I so what is a BTP? BTP is form of a cache, but for like for branch prediction. So it predicts whether a branch target is correct or not for a certain branch. So what will be the branch penalties? So one case is the branch is present in BTP, but the prediction that has been given is not correct. It is a misprediction. That will be one penalty. Another penalty will be, in this case, branch is not found in BTP. So it is not present in BTP, and the prediction is, and it is a taken branch. Another will be branch found in BTP, not found in BTP, and it is also a non-taken branch. So in each case there is a separate penalty. So in this case there is a penalty of 2, because the prediction taken is false. So that is a 2. Another is a taken. If it is a taken branch, the penalty will be 2, and if it is a non-taken branch, the penalty will be 1. So what will be the value? So if we calculate this, what is given as the like 85% of the branch are present in BTP. So the first one will be 0.85 into, it is a misprediction, that is 0.15 into 2 plus branch not found in BTP, that will be 0.15. 75% of the branch are taken into 0.75 into 2, and the last one will be 0.15 into 0.25 into 1. So it will come around 0.5175 clock cycles. So let me explain this again. What is a BTP? BTP is a form of a cache. It is a form of a cache. So you know what happens in cache, that whenever we fetch a data from a memory, we check whether it is present in a cache or not. Similarly, in case of branching, it checks whether the target branch address is present in the branch target buffer or not. So what can be the case? What will be the best case? Branch is present in BTP and the prediction that is given there is correct. So that is the best case. In that case, there is no penalty. Now let's come to the other cases. So the branch is not is present in the BTP, but the prediction is wrong. So in that case, the penalty is 2. In that case, the penalty is 2, as we have mentioned here. Next is the case branch is not found in the BTP, but and the taken and next the actually what happens is it is a taken branch. In that case also, the penalty is 2. And the last case is branch is not found in BTP and it is a non-taken branch. In that case, the penalty is 1. So what will be the branch penalty? Branch penalty will be totally, it is given as 0.85% in BTP. So 0.85 in of the branches are present in the BTP. So it is 0.85, 0.15 because it is a 15% prediction are incorrect, and 2 is the penalty, that is the cycles that will be stalled. Now branch not found case is 0.15, that is 0.15 instructions are not present in the BTP. 0.75 are the branches taken into 2, and the last one is branch not found. Branch not found is 0.15, 15% are not present, 25% are non-branch instructions. If 75% are branch taken, then 25% are non-branch, and its penalty is 1. So if we calculate this, it will come out to be 5175. Ask. Microphone is open, you can ask. Yeah, I'm explaining that. Yeah, I'm coming to that, don't worry. So this one was the last question. If you have any doubt in this question, you can ask. Okay, so let's come to his Shrikant's question. Can you scroll, sir? Can you scroll all question once? Yes, sure. I will come to your question, Sashikant. Wait, I will solve it. Don't worry. Because if you have any doubt in any question, you can ask regarding this. Yeah. Uh, what is greedy cycle? Greedy cycle. Okay. Consider a pipeline processor where interstage pipeline are assumed to be 0 and the stage delays are specified in nanoseconds. Which of the following will have the highest clock frequency? Fine. You have given the stage delays. Okay. So you have seen today's lecture, right? Today after this you can solve it. So what will be the like clock period? The one with the maximum value clock delay. So like let's go to all of them. For A we have 1 comma 2 comma 2 comma 1. 1 2 2 1. 1 1.5 1.5 1.5. 0.5. So which of the following has the highest loss frequency? So which has highest, which has highest frequency? So what is the concept? Frequency is equals to 1 by Cp. So the one with the lowest clock period will have the highest frequency, right? So what will be the clock period of this? Max of 1 2 2 1. So that will be 2. What will be the clock period here? 1.5. What will be the clock period here? What is the maximum here? 1. And what will be the clock period here? Maximum is 1.1. So C will be the answer, because it will have the it has the minimum CP clock period, so it will be the have the highest frequency. Understood? What lecture 41 slide 31? What what are you telling? So it is given in that slide number. You can ask. The mic is open. Okay, let me check once. What is there? So let me open the open that one once. Uh, slide 31. So 41 is the first lecture of that, like what number lecture? Oh, you didn't get how to calculate mal and how to get greedy cycle. Okay, so I have discussed it in that week's one. Please check it. I have discussed it in that video of lecture 8. So you can check that video. Okay, it is a very complicated process. I have done it, and now if I like that lecture had went that day around 1 hour 40 minutes, like 1 hour 20 minutes. So that took a lot of time. That greedy cycle problem. So it will now take lot of time. You have to redo it. So please check that one, and if you have any problem you can ask in the like if next class it will be a shorter class, so you can ask next week if you like if you have still doubt about it, right? Yeah, the week 12 lecture will be there. So next week there will be there. Next week the session will be shorter, like there won't be much questions, so you can ask those questions then. Okay, so we will meet again in the next class, like next week. It will be the last one. So, okay.